The fundamental difference between pulsed wave and continuous wave Doppler lies in how the ultrasound signals are transmitted and received, which dictates their ability to pinpoint the location of blood flow versus ability to measure high velocity blood flow. Here is a breakdown of how each modality functions and where they are most effectively deployed in clinical echocardiography. Pulsed wave Doppler utilizes a single piezoelectric crystal that alternates between sending and receiving ultrasound signals. It emits a brief pulse of sound, waits for the echo to return, and then emits the next pulse. Range resolution. This is the defining advantage of pulsed wave Doppler. Because the timing of the returning echo corresponds to the distance, you can place a sample volume or gate at a precise depth. The machine only analyzes Doppler shifts returning from that exact location. The aliasing limitation. Pulsed wave Doppler is restricted by the Nyquist limit. If the blood flow velocity is too high, typically more than 1.5 to 2 meter per second, the machine cannot sample the returning signal fast enough. The waveform wraps around the baseline, a phenomenon known as aliasing, making it impossible to determine the true peak velocity. Clinical application. Pulsed wave is used when location is critical and velocities are normal or low. It is ideal for assessing left ventricular outflow tract velocities, profiling mitral valve inflow E and A waves for diastolic function, or mapping the precise origin of a regurgitant jet. Continuous wave Doppler uses a transducer with two separate crystals. One continuously transmits ultrasound waves, while the other continuously receives the returning echoes. High velocity measurement. Because transmission and reception are continuous, there is no waiting period and therefore no Nyquist limit. CW Doppler can accurately measure extremely high velocity blood flow without aliasing. Range ambiguity. The primary limitation of CW Doppler is its inability to pinpoint exactly where the velocity is occurring along the ultrasound beam. It records all Doppler shifts along the entire length of the beam. Clinical application. CW is essential when precise velocity quantification takes precedence over depth localization. It is the standard for measuring peak gradients across tight stenotic walls like severe aortic stenosis, or calculating right ventricular systolic pressure from a high velocity tricuspid regurgitation jet. Here are the key differences at a glance. Crystal configuration. Pulsed wave, single crystal alternates send and receive. Continuous wave, two crystals, one sends, one receives. Depth location. Range resolution, exact depth is known for pulsed wave Doppler. Range ambiguity, exact depth is unknown for CW. Velocity limits. Low limit subject to aliasing for pulsed wave Doppler, while no practical limit, no aliasing for continuous wave Doppler. Primary echo utility. Pinpointing flow location, example LVOT pulmonary veins for pulsed Doppler. Continuous wave Doppler, quantifying high velocities like aortic stenosis or TR jets. Audio-visual profile. Clean spectral envelope for pulsed wave Doppler. Filled-in spectral envelope for continuous wave Doppler.